In this lecture, we're going to dig into the free radical halogenation reaction, start to be able to build up the skill of being able to predict products of this reaction, and then again, being able to use the reaction to make some sort of target molecule. So getting our notes in front of us now. What I want to do is just remind us what we're trying to do with this reaction. We're taking some alkane. I can spell alkane. We're adding it to a halogen source. It could be one of 4 potential halogen atoms, or halogen sources, excuse me. And then we apply either heat, which we show as a triangle, or light, which we show as H nu. So it could be either one of those. I'll even put or on the line for us. And we're going to make some new haloalkane. And that's what we want to be able to predict. We want to be able to draw the structure of the new haloalkane, figure out what the question mark is. And if you want to balance the equation, you could write plus HX over here, and then maybe you have your alkane attached to the H that gets lost. All well and good. But what we want to be able to do today is predict the products for this reaction. So let's say that we, I'll leave this up, sorry if I was moving too fast. Let's say we have ethane, which I'll write out as sort of an abbreviated Kekulé structure. And I'm going to add that to, or mix that with chlorine, diatomic chlorine, and I'll apply triangle, some heat to it. And what I want to be able to do is predict the products. Now, for the most part, we're only going to see one chlorine atom add to the alkane. And it could add at multiple spots, and we'll get to that towards the end of the lecture. So as the molecules get more complicated, there are just more places, more unique places and positions you could put the halogen atom on, which gives rise to mixtures of products. But what I want to do is qualify before we get too deep into here that when I say predict the products, we're going to have monohalogenated products. Now, that's not a term that I want you to be intimidated by. All I'm saying, I'm actually making your life easier. All I'm saying is ignore possibilities where multiple halogens could add. So that's what that term kind of suggests to us. So whenever I say predict the products, and I think on the exam, I'll be sure to clarify that and say predict the monohalogenated products in the process below. Okay. Now, what makes this somewhat challenging is that we could put the chlorine atom at multiple places. Fundamentally, what we're doing is replacing a hydrogen atom, in this case, with a chlorine atom. So it could be any of the other halogens. So we could replace the hydrogen atom with bromine, chlorine, fluorine, iodine, whatever. Now, what's nice about this first example is that if we draw out the full Kekulé structure without wedges and dashes, and wedges and dashes usually don't matter too much, but without wedges and dashes, what I want to notice is right away that replacing an H with a Cl forms only one unique product. So this is a nice example to start with because we're only going to have one product. So what we can do is pick any of the hydrogen atoms and replace them with chlorine because any of them are fair game for this reaction. And like you can pick any one that you want. I'm just going to pick the one pointing up and to the right on the right-handed carbon atom. And I've got my product. Okay, so we replaced one of the hydrogen atoms with a chlorine atom, and this is our product. In this particular example, it's the only product. If we would have put the chlorine atom at any other hydrogen position, this might take some rolling around to prove to yourself, but we actually would only form one product. That is to say, if I have the product shown here, or if I have this product where I put it in the upper left position versus this product, these are the same because I could undergo free rotation over carbon-carbon single bonds or just simply roll the molecule around in space to get them to superimpose. So these are the same product. Even though there are 6 positions, there's only one unique product in this case. So even though there are 6 times H atoms that can react, only one unique product forms. So not too bad. You draw the molecule out, you find the hydrogen atom, and you replace one of the hydrogen atoms with one of the halogen atoms that comes in as X2, right? Well, where it gets to be a little bit more complicated is if we just make the molecules, the starting molecules themselves, more complicated. So I've now got propane. I just went 1 carbon up, right? I went from ethane to propane. I'm going to add to that Br2. I'll go ahead and write Br2 as the diatomic atom, and I want to, I'll use light in this case instead of heat. It's going to do the same thing. We're going to replace hydrogen atoms with bromine atoms. Now, the question is, predict what goes on the right side of the arrow, or predict all unique monohalogenated, oh boy, running out of space, halogenated products. So all means multiple. We could have, I guess we could have 0, but we could have as little as 1 or 0. And we could have as many, we could have many. But we want them to be, we want to get all of them, and we want them to be unique. That is to say, we have no duplicates. And then monohalogenated, again, is to just make your lives easier. The products we want to have only have one, in this case, bromine incorporated, as opposed to multiple bromines incorporated, which may be possible in some cases. Okay, so we're using light in this case. That doesn't change the outcome. We're still replacing hydrogen atoms with bromine atoms. But what does change the outcome is the fact that we now have a different starting molecule. We have propane instead. If you notice, propane, instead of having 6 hydrogens, has 8 hydrogens. Okay, no, that shouldn't be that big of a deal. We're just trying not to break the octet. Now, what I want us to start thinking about is the symmetry of the molecule. The left-handed carbon is a CH3, and the right-handed carbon is a CH3. Additionally, due to some bilateral symmetry that splits the molecule in half, the hydrogen atoms attached to the left-handed carbon are in the same environment, or sort of the same, they kind of look the same as the ones on the right. If you replace any of the hydrogens on the left-handed carbon with any of the hydrogens on the right-handed carbon, you'll get the same product, okay? So that is to say, if you replace them with a bromine atom in the presence of light, you could form this product where I replaced one of the left-handed carbons with a bromine, one of the left-handed hydrogens with a bromine, excuse me, or this carbon. They are the same molecule. You could just rotate one around to get to the other. So we need to cross this one out. We don't want any duplicates. So the first structure works, but the second structure is a duplicate structure. Now what I want us to recognize is that the middle carbon has 2 hydrogen atoms. These are different looking to the bromine atom than the other 6. So replacing one of the 6 would give rise to the bromine atom being on the end, either the left or the right end, pointing in any direction, assuming it's attached to that carbon correctly. But we could also replace one of the hydrogens at the center position of our molecule to get something like this. And that would match, I guess we would highlight green. Now, highlighters sort of work what I prefer to do is actually label the various types of hydrogens. So I'm going to label this hydrogen as HA, and replacing that hydrogen with HA would give product A. So we have product A and we have product B, where B results from replacing this hydrogen. Well, in the case of product B, we could have used either of the two hydrogens. So I'm going to label the second hydrogen in the middle carbon as hydrogen B. So my point with using these labels, it's kind of helpful because it reminds me that, hey, I could replace either one of the HBs with a bromine atom and I would get the same product, which I've labeled as product B. Okay, now what about A? Well, I've labeled one of the hydrogens on the left A, the one that seemingly directly correlates to product A, but I could have replaced this one and gotten product A and this one and gotten product A. And you know what? If I put the bromine on the opposite side, I can roll the molecule over to show it's the same. So if I put the bromine at this position, or this position, I get the same product in every case. Okay, so this is where the challenge comes in with free radical halogenation reactions. Fundamentally, you're just finding hydrogen atoms by converting, thinking about bond line structures. You don't have to draw the hydrogen atoms, but they're there. Their existence is implied, as we say. But then you have to recognize which hydrogens are considered, quote, the same, that is, replacing them with a halogen would give rise to the same product, and which are different, so that you can accurately predict the total number of products without having any duplicates. Okay, so that's sort of the major goal. And where the challenge comes in is looking at complicated molecules and making sure not to miss one and making sure to have no duplicates. So let's go through another example. If I pick I2 in this case, let's go back to heating. So we have iodine. I want to put a question mark here. The task is the same. Predict all unique monohalogenated products. And so one thing you can do until you get really comfortable with this is to just take the starting material and draw out the hydrogen atoms. And you'll get better at this and you'll get faster at this. Trust me, it just takes some practice. And then you'll be like, well, I've seen what it looks like when I have an isopropyl group. I've seen when two methyl groups are sometimes the same and sometimes different. You'll see all of this stuff and you won't need to redraw all of these things. But to get started, let's go ahead and work through this example. Okay, now what I want to start by pointing out is that the methyl group, or the CH3 at the end, let's call that A. If I replace hydrogen A with an iodine, I would get this product. Now, due to carbon-carbon free rotation, carbon-carbon sigma bond free rotation, I could spin that around, and any of these three hydrogen atoms that I've labeled as HA could give rise to product A. So I'm going to label this as A. That's my product A. And you could label it anyway. You could start from the left and work to the right. This is just how I organize my thoughts, especially when I'm not familiar with the molecule. Now, the next carbon has hydrogen atoms, two hydrogen atoms, and both of these, replacing either of these would give rise to the same product. You might say, well, Willoughby, isn't that product chiral? I'd say, great, astute observation. You actually do recover the product as a racemate. Remember I said that when we're trying to synthesize things in the lab, if we don't have something that starts off with chirality, we're going to form a racemic mixture. That's great. That means you don't have to worry about wedges or dashes. Just draw it with a straight line, communicates to everybody that you have a racemic mixture that's formed. Both enantiomers are formed, both equal compositions of wedges and dashes. Let's not even bother with wedges and dashes. Wonderful, right? Okay. So next we can move to the next carbon, which is C. C is clearly different. Replacing C gives clearly a different product than anything else. You have the iodine sort of sandwich between the two one carbon chains, or the two methyl groups. Now let's get to those two methyl groups. What I want you to notice about replacing a hydrogen up top on one of the CH3s is actually the same as replacing one down at the bottom, again due to free rotation. That is, if I replace a hydrogen at this CH3 position, it could be any of those three hydrogens. that's the same as if I replaced hydrogen down below. Now, how can that be? What I want you to do is recall that we have free rotation over carbon-carbon sigma bonds. And I guess, yeah, that's the one that would spin. If that one spins, we'll flip the iodine up and we'll actually get a structure that's superimposable on the left. And that's how we tell that molecules are the same, remember, is if we can do something with free rotation or rotation in space to make it so molecules can overlap, they're actually identical. So in this case, what I've drawn on the bottom right is actually a duplicate structure, whereas this structure now is D. And I've shown that to get to product D, I could use this hydrogen, and it could be any of those three hydrogens. It's a methyl group or a CH3. But similarly, down below, we've got another CH3 that could also provide that product D. Now compare product D to product A. If I compare D to A, the reason why I'm bringing up A is because in the case of A, we have another CH3, but you'll notice this CH3 is different. It doesn't have, due to symmetry, it just isn't able to kind of give rise to the same products. So in the case of this molecule, we have two different types, I guess, of CH3 groups, and substitution at one of them on one side is different than substitution at the other two. But the other two, which give product D, are the same. We could introduce a plane of symmetry to make it so that the left side and the right side are the same. So we have a plane of symmetry here. We would then have an HA, an HB, and an HC, and that's it. Anything else would be a duplicate. So if we took this molecule, let's actually draw a reaction out. We'll get fluorine in the game. So fluorine time, and we'll just use heat maybe. We could replace HA, and we could replace HB, and we could replace HC, but anything else would become a duplicate structure. And so again, that's sort of the challenge here, is to look at various examples. Now, what about double bonds? And the answer is ignore. You need to ignore carbon-carbon double bonds. They don't participate in this reaction. And you might be like, well, why? And we have very deep answers for that. But this is an experimental science. So what I'm getting at is if you see something like this, okay, and you react this with Cl2 and light. So the Cl2 and light, that's not necessarily a change. But I get it. There's a bunch of H's here, 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 all around this benzene ring because it has alternating double bonds and single bonds. None of those participate in the reaction. So this is a case where we only have an HA and an HB. I'm just going to go from left to right, and we're only going to have two products, Cl present and the central carbon, and then a Cl present at the far right carbon. And we only want to do monohalogenated products, and we want to do so without repeated structures. Okay. So I guess I worked kind of quickly through that. Let me just, sorry, let me get that in front of you again. I feel like I just went very quick. And while I'm doing that, I can wrap up the lecture. So sorry to cut out the notes on that. What we looked at today, or in this lecture, was how to predict the products for free radical halogenation reactions. We saw several examples. There's more examples in the discussion problem sets. Practice, practice, practice. It'll be hard at first, but then you'll start to see things you've already seen before. Even though there's an infinite number of molecules, bond line structures that I could put in front of you, there's not an infinite number of scenarios where, due to symmetry, these methyl groups are the same or they're not the same. So just practice, look at examples, ask me questions, and I can help you kind of rule out when you've got duplicated structures to make sure that we're following the rules and providing only the unique products and making sure we don't miss any.